Okay, so thanks for joining me today. Could you tell me your name and your day job?
So yeah, I'm Louis Ledoux. Right now I'm working at BSC, Barcelona Supercomputing Center, and UPC, Universitat Politécnica de Catalunya, where I'm doing currently my PhD. It's a fourth year in computer architecture labs, and I'm personally I work on arithmetic optimizations. Yeah.
Cool. So, what made you want to get involved? Because actually, we met through Guillaume, who I know from Valencia, and I invited him to be involved in MPW1 with me before the course was even there, and you collaborated with him.
Yeah.
But then since then, you've worked through the course and submitted again on MPW5, or did you do another submission as well?
So we did 1 and 4 with Guillaume with
Yeah,
the watch, the ASIC
yeah,
watch, and then he was not available for the fifth, and I learned enough for trying on my own. So
yeah.
I submitted on the MPW5 the matrix multiply unit.
Cool. Yeah. So why did you kind of want to get involved?
So the first step was okay, like you told, Guillaume showed me that, and I was like, okay, I know only digital design and FPGA. He told me there is an opportunity to learn ASIC with a nice course, so okay, I jumped in. In the beginning, it was not easy, but I really wanted to learn. Like I like to learn by doing the stuff, so I had to do the thing. We were two, so it was easier to get involved, to have the hands on. And in the end, I liked a lot, so I kept submitting again, and it was mainly to learn actually, and to extend my field, because right now FPGA I might know the base. I mean more than the basis, so I want to extend my knowledge, and going to the ASIC field was, I think, a nice opportunity. So yeah.
Cool. So what part of the course did you enjoy the most?
Um, so I like in the end, like the last step, no, the antelast step, the project form, when you just have your design that compiles in minutes, and after you have a huge, I mean, what I consider huge, GDS, when you can that you can explore, and if this is a result of design that also has a working simulation. So you are like you have pretty much everything, and it's very enjoyable. So you can work in your GDS while knowing it might work, uh, thanks to the simulations.
Fingers crossed. Well, we have a bit more confidence now that we've got
Yeah,
MPW1 back.
yeah,
And you're still waiting on the MPW1 chips, which seem to be lost in transit, right?
yeah, but they will arrive, and
Yeah.
otherwise Guillaume will send them in priority letter. He told me.
Yes. Guaranteed
Yeah.
delivery. Um, so, yeah, let's talk a little bit about the project that you just taped out on MPW5. Can you tell us a bit about that?
Yeah. So I'm right now on the GitHub README. I think I will follow a bit what I've put there. So first of all, it's a generator. It's not a one design, so it's a command line interface generator form that generates systolic arrays that perform matrix multiply, or GEM for the HPC people. GEM stands for General Matrix Multiply, I think. So you can choose the size of the array, the arithmetic that comes in, the data type, I mean, that range from the known one, like IEEE 744, single, double precision, also bfloat, or novel ones like POSIT arithmetic. And it's not limited to that. Actually, you can put every size of fields you want. If you want a mantissa of 70 bits and exponent of, I don't know, 14 bits, it's possible. So it allows you to generate all these matrix multiply unit, and then it wrap all of that in XC stream wrapper. So you can connect that to many things. So it's convenient. On top of that, there is in the processing elements that built these historic arrays, this historic array, each processing element perform a dot product, and each dot product is fused. That is to say that there is no rounding between every accumulation. It's like when FMA was invented, there is no rounding between the multiplication and the addition. So it avoids round-off errors that can happen between these two steps. So you need an internal extended precision to allow to do this round-off without this non-round-off without errors. And so this is another feature. I also leverage Flopoco. Flopoco is developed by people of INRIA, France, Lyon, called Florent de Dinechin, that stands for floating point cores that permit to do some automated data pass, automated pipeline data pass. So you just have to describe the behavior of an addition or shifter or some stuff like that, and it will and then you specify the target you want to reach, like this FPGA at this frequency, and it will create the necessary and sufficient insert the flip-flops that you need and no more. So that was for me very convenient to explore these many arithmetic parameters we need to build this entire function. That's pretty much everything. Yep.
So maybe it would be helpful to give us a couple of example applications for when this would be useful.
So yeah. So as you might know, matrix multiply can be used everywhere. So that's why people optimize a lot this kernel, so they can do AI with gems or weather forecast simulation with matrix multiply. But everybody is constrained with the same data type. So sometimes for weather forecast, you need a reproducibility. Therefore, you will do the matrix multiply with 128 bits data type inside. Maybe it's too much. You only needed 96. So in millions of operation in a supercomputer, this can result in a huge waste of energy, or it's not needed. That's all. So here I think I provide a way to generate only what is necessary for performing the good gem and save energy in the end. So by doing the good computation when it's needed, you can save energy and eventually gain performance operations per second. So yeah, and in AI it will be the exactly opposite. You will reduce a lot the precision because they are resilient. The neural networks are resilient to noise or to low precision, so you will try to reduce a lot so you can put more processing elements in the same hardware because they are smaller data paths, and then you gain performance if you care less about energy. Yeah, the two examples are that very low precision or very big, and when you need reproducibility also.
So I'm just checking the GDS that we put in the group submission, and that looks like it's 600 by 600 microns.
Yep.
So what was the configuration that you gave for your generator?
So it's a very small one. It's a 3 by 3. So I'm quite surprised it does a lot. I'm not too surprised, but I will explain why after. And for instance, I've been able to do 64 by 64, which start to be like 4,000 processing elements in FPGA. Okay, they are not the same technology. and stuff like that. But 3x3, I'm surprised it's as big as the sock that is above the systolic array. So the thing I think is not well done for MPW5. It's because I've made a lot of optimizations for FPGAs. While I'm still agnostic to the target, it will put a lot of flip-flops. And I know that they are expensive. Like I think you told that there are 30 transistors in Sky 130. So that's why I
they're
think
among the biggest standard cells, aren't they?
yeah, it makes the thing expand a lot while not being necessary. And I put all of these flip-flops for something that is called HSSD. So it's a mechanism that I add that allows to the result to output while the input arrive. So to pipeline basically, but at the cost of a lot of flip-flops. So because I was targeting 20 gigabyte links, I needed this pipeline to not make this inefficient. And I think in a case of 3x3 thing in ASIC where I don't have a high-speed link, it was unnecessary to have this output mechanism, and I could have avoided putting a lot of flip-flops. But there was room, and I knew it was working because it's the one that does the more and the simulation. So I went with the design with a lot of flip-flops, even if it's not the most optimized.
So will you be doing a more ASIC targeted version in the future, or are you kind of happy to leave your experiment as it stands?
So for the future, I would like to compare this one with the same but with another arithmetic, because a lot of people are fighting to know which arithmetic is the best right now. So I can say this arithmetic is bigger area. Yeah, but I would like personally to do submission. If you can have access to my README that I'm on Rapid TERAS, I've put.
Yeah, I'm looking at it.
In the middle, I've put a command line when I speak about Flopoco below the figure 3. And at some point, there is written a target is equal to Kintex 7, for instance. So it means I generate data path for this PGA. So if I'm motivated enough, I create a target Sky 130, and it will create the data path for this technology.
Cool.
And yeah, that will be nice, generating exactly for this ASIC process node. But it is not as easy as I think, because I have to deep dive in all the cells, and like you told, 2 gates can be faster than 1 gate, and I didn't know that, so I'm pretty sure a lot of things I don't know.
Ideally, the tools work that out for you.
Yeah.
Yeah, so would you recommend the course to somebody else?
Yes, of course. I would, and I think I will. The thing is, yeah, you can learn very fast. Thanks. I mean, the course itself is very self-sufficient, but on top of that, you have the community behind. Not only the Discord, but the Discord helps a lot. People are happy to help, like in seconds, and you can have how to say. Reviews on what you did in a few seconds. The simulation didn't work, check that. Very nice. There is an explanation for every word. You can get an ASIC in 24 hours. I mean, from source code to GDS. So yes, I will definitely recommend the course. Yeah.
Great. And any final thoughts you have?
I was not prepared for that question. So no, maybe not. I don't have. Let's see in MPW6 what we do. Yeah.
What happens?
Yeah.
Cool. Okay. Well, thanks very much for your time, Louis.
Thanks to you.